Okay, so today we'll be talking about 3D geometry. Basically, we'll be going over planes and 3D objects, except we won't go too complicated. It will mostly be stuff like spheres and cubes and whatnot. Okay, so first, let's consider a plane. So, a plane, I'm not talking about like an airplane, whoosh whoosh, but instead, imagine a piece of paper. Now, imagine that this piece of paper extends forever in all four directions. That is a plane. And this is a two-dimensional figure. It doesn't go up or down. And just consider it like a table in space, and anything that exists on the plane you have to be able to place it on the table. And this is a 2D space. If you want to talk about a three-dimensional figure, that would be known as a space, incidentally. So for that, just imagine a cube that continues on forever in all directions, and technically this would just be everything. And since a space is everything, we don't really use it that much because there's not really much point to it. Just to revisit something we talked about, before we defined two parallel lines as just two lines that never touched. And in this case, we're considering line to be like a line that extends in both directions indefinitely. But that definition was not entirely true because, at least in 3D geometry, in 2D geometry, you can keep that definition two lines that never touch. But in 3D geometry, it is another caveat. There are two lines that never touch and are on the same plane. Um, so you can imagine it as two pencils. If you put them both on the table, and they are parallel to each other, then of course they're parallel. But then if you take two pencils in a space and you put them parallel but then start rotating it, even if these two pencils or lines will never touch, they are not actually parallel. So I'll try and draw it. Pencil and a pencil in space. If you start rotating it this way, these two pencils, even though they don't touch, they aren't exactly parallel, and these are known as skew lines. Honestly, this will probably not come up in any math competition, but it's something to know, I suppose. Um, now, just a few properties about planes. First, if you have a plane and a line, um, there are three things that can happen. Um, Either the line could be on the plane, like this, the line could intersect with the plane, like this, or it could simply be parallel with the plane and, except not on the plane, just underneath it or something, and just never touch it. And since the plane extends in all four directions, there's no such thing as a line that's skewed to a plane, because if you think about it, you can just rotate the plane however you want, and it's still going to be the same. Also note when I say rotation, I mean rotating it this way, um, not like rotating it this way. Now, how do you find a plane? Um, a plane can be formed with any 3 points in space. And if you think about it, any two lines in space, any 2 points in space, you can create a line with it. And then the third point will be, imagine that you attach a sheet of paper to this line, and then the third point will just be you rotating the sheet of paper uh, in a way that it also intersects with this point. So if you think about it, imagine this line is a stick. You glue a sheet of paper to it, and then you're rotating this around until it somehow intersects with this third point. And incidentally, this is why like a lot of stools have three legs, because if you have three legs, you're guaranteed to have a plane, so it's never going to wobble if it has three legs, even if it might be tilted to one side. And because of this, since any 3 points will be guaranteed to be on the same plane, there's something called coplanar, um, where you have four or more points on the same plane. So if you have, like, let's say these points are all on the same plane, we say that these points are coplanar. Now that's enough about planes. Let's talk about 3D objects. So let's start with a simple one. How about a cube? Now there's two semi-important things for 3D objects, like two properties, I suppose. First, surface area. So imagine you cover this cube with sheets of paper, so all sides are covered. The combined area is equal to the surface area. And normally to find this, you just add up all the areas, treating them as 2D objects, add them all up, and then you get surface area like that. And the second one is volume. You've probably heard of it. It's basically the measure of space. Like, imagine you hollow this out. Volume is just like the measure of how much water you can pour inside this object. Now, let's just go over a few simple shapes. First, how about a sphere? So a sphere, actually I just draw this as a dotted line. The radius is the distance from the center to one of the edges. This is the radius. And then the sphere is defined as the set of all points in a plane which are fixed distance from the given point, which is the center. And this is basically a ball. You probably don't have to go too much into it. Anyway, surface area is 4 pi r squared, or pi d squared, either one works. Surface area, I'm just going to call it SA. And volume is equal to 4/3 pi r cubed. Next on the list, we have cubes and boxes. Technically, a box is defined as a rectangular prism or a right parallelepiped. Uh, yeah, so just you can just call it a box or rectangular prism. So a cube, it's basically dice, squares on all sides. And then if the side length is s, then the surface area is equal to 6s squared, because just 6 faces, and then area of each face is side squared, and then volume is equal to side cubed. And incidentally, a diagonal, like from one vertex to the opposite vertex, is equal to, I just call the diagonal, call it d. It's equal to s times square root of 3. And you can prove that using Pythagoras. And then a right parallelepiped, or a box, it's basically the same thing, except not all sides are the same. And there's a length, a width, and I'll call it a height, I suppose. The surface area is equal to 2LW plus LH plus WH, on just adding up all the faces, which are rectangles, which you can figure out easily. And volume is just length times width times height. Simple enough. Next, we have prisms and cylinders. Now, a prism is a figure which two bases are parallel and they're congruent, and the sides are parallelograms by connecting the vertices of the bases. So what does that mean? So let's say you have, I don't know, an octagon, and extend it like this. And on the other side is also an octagon that is an octagonal prism. Uh, and then basically to get the surface area, just add it up. Um, Add up all these rectangles, so length times width, and then add the area of the two faces. And then volume is equal to the base here times the height. And I'm just considering this the height. Anyways, a regular prism is if the face is a regular polygon, which as you remember is basically a polygon with all sides and interior angle the same. And the height is the perpendicular distance between bases. So don't try and draw a diagonal and say that's the height. That's not right. And a right prism is when the sides are perpendicular to the bases. So technically, if you have something like this, where it's kind of slanted, that's still technically a prism, except it's not a right prism because it's not perpendicular here. So a right prism is when the sides are perpendicular to the bases. And those are the most common prisms. Usually you won't see them slanted. Anyways, a cylinder is basically a prism, except you have a circle as the face instead of a polygon. And it's basically the same. The surface area, it's equal to 2 pi h. 2 pi hr, where this is height, radius is here, and plus 2 pi r squared. And if you think about it, that makes sense. It's a circumference times the height here, plus the two faces. And then volume is equal to pi r squared times height. And you can think of it as taking a flat circle and stacking it until it reaches its height h, and that's how you get the volume there. Finally, we have, well, I guess not really finally, there's a bit more after, but pyramids and cones. So a pyramid is, you have a polygon at the bottom, and it all converges as a point at the top, basically. And interestingly enough, the volume of this is equal to 1/3 base times height. So basically, if you have a prism, it has actually had the same volume as 3 of the pyramids, assuming they have the same base and the same height, which is a bit odd, and well, there is a proof for it, and we won't go into it, but you can just take it as a fact. And a right pyramid is basically when the vertex here is directly above the center of the base. And surface area is equal to area of base plus 1/2 slant height, I'm just going to call it S, times perimeter of the base. So P is the perimeter here, and the slant height is equal to this length here. And a cone, well, you've probably heard of it. It's basically the same, except you have a circle at the bottom. And then a surface area is equal to pi r s, where s is the slant height here, plus pi r squared. And incidentally, s is equal to square root of h squared plus r squared, and you can just prove that using Pythagoras. And incidentally, you can also do the same thing with the pyramid too, using Pythagoras. Anyways, the volume is also equal to 1/3 pi r squared h. So basically, if you have a cylinder and a cone, you can fit 3 of these cones inside a cylinder, assuming they're the same height and they have the same radius, which is a bit funny actually. Now the final thing to talk about is polyhedra. So a polyhedra is a solid figure whose faces are all planar polygons. And there's no curved surfaces in a polyhedra. And that's basically most, like when you think about it, just everything we've gone over except for cones and cylinders. Now, a regular polyhedra is a polyhedra whose faces are all congruent regular polygons. Now, there's a lot of them, but let's just go over a few of the simpler ones. First, tetrahedra. It's basically sort of like a pyramid. It has 4 faces, which is why there's a tetra. Anyways, all these faces are equilateral triangle. Next, you have a hexahedron, which is basically a cube. And then next, you have an octahedron, which looks something like this. And has 8 faces, and anyways, the pattern basically goes on with the prefix based on the number of faces. And to be honest, you probably won't go into these regular polyhedra too much, but at least know the first 3, I suppose. Now, to be honest, I kind of went a bit long for a relatively simple lesson, so I'll leave you with one quick question. Consider a unit cube where each side is equal to 1. A, B, C, D, E, F. How many do I need? 2 more, G and H. Where all these are just points. All these are vertices. Now consider that this center of face ABCD is X. So basically A, B, C, D, E, F, G, G is somewhere there, and H. So like that basically. So find Fx. Anyway, just a simple question to end it off today. And see you next week.